There had been a long stretch of human thought in which empty space was assumed to hold nothing at all, no substance, no energy, no behavior of its own, simply the absence against which everything else was measured. For most of that stretch, the question of what occupied the gaps between things was treated as a question with an obvious answer. And the obvious answer was nothing. The idea persisted across many civilizations and many centuries without serious challenge, carried forward less because anyone had tested it than because no one had found a reason to doubt it. Aristotle, writing in the 4th century BC, gave this assumption its most influential philosophical defense, and in doing so, made emptiness itself the subject of an argument rather than a casual impression. He proposed that a true vacuum, a region containing absolutely nothing, could not exist in nature, because nature abhorred such a condition and would rush to fill it the instant it appeared. His reasoning rested on his broader theory of motion, in which objects moved through a medium that resisted them, and without that medium, he argued, motion itself would become incoherent. A body moving through nothing would either move infinitely fast or not move in a way that could be described at all. The conclusion he drew was not a minor aside, but a structural pillar of his physics, one that would be carried into medieval scholarship and treated for nearly 2,000 years as settled. What is worth sitting with is how reasonable this looked from the inside. Aristotle was not guessing carelessly. He was working from the only physics available to him, a physics built entirely on observations of falling stones, flowing water, and the visible resistance of air, and within that framework, a region with nothing in it to push back against a moving body was not just unfamiliar, it was logically unstable. The horror of the vacuum, as it came to be called, was not superstition dressed as philosophy. It was a careful conclusion drawn from a coherent, if incomplete, picture of how the physical world behaved. That picture held for an extraordinarily long time, and it began to crack only when instruments capable of producing something close to a vacuum entered the world. In the middle of the 17th century, experimenters working with mechanical pumps managed to evacuate enclosed vessels to a degree that earlier centuries could not have achieved, and the results unsettled the inherited consensus without immediately replacing it. Sound failed to travel through the evacuated space, flames extinguished. Small creatures placed inside such chambers did not survive. These were not the behaviors of a space secretly full of some invisible substance rushing in to prevent emptiness. They were the behaviors of an actual absence, and the philosophical confidence that nature could not tolerate such an absence began, slowly and without any single decisive moment, to dissolve. It was Isaac Newton, working in the later 17th century, who gave empty space its next great identity, one that would last far longer than Aristotle's had, even as it discarded Aristotle's central claim. Newton did not treat the vacuum as impossible, he treated it as foundational. In his framework, space was not a void to be feared, but a fixed, absolute stage against which all motion could be measured, a container that existed whether or not anything occupied it, unchanging, uninfluenced by the matter moving through it, and entirely indifferent to events taking place within it. Time, in his system, ran alongside this absolute space in the same unaffected way, a separate and equally fixed backdrop. Together, they formed the arena in which the laws of motion and gravitation operated, and that arena itself was never an actor in the drama, only the stage on which the drama occurred. This was an immense conceptual achievement, because it allowed space to be empty without being incoherent. Newton's vacuum could exist, could be measured, could be reasoned about mathematically, all without violating any principle of motion, because motion in his system no longer required a resisting medium to make sense. Bodies moved according to forces acting upon them, and an empty region offered no contradiction, only an absence of resistance. For more than 2 centuries, this was the inherited picture passed from one generation of natural philosophers to the next. Space as an inert container, present everywhere, doing nothing, asking nothing, simply holding the universe in its fixed and silent geometry. Yet even within this Newtonian picture, a quiet discomfort persisted, one that would eventually produce the 19th century's most determined attempt to give empty space a physical substance after all. The discomfort came from light. When physicists in the early 1800s demonstrated that light behaved as a wave, the immediate question that followed was unavoidable. A wave needed something to wave in. Water waves needed water. Sound waves needed air. and a wave of light traveling across the vast emptiness between the Sun and the Earth seemed to require some medium filling that emptiness, some substance through which the oscillation could propagate. Physicists named this hypothetical substance the ether, and for the better part of a century they treated its existence as a near certainty, building increasingly elaborate models of what it must be made of and how it must behave in order to carry light without otherwise interfering with the motion of planets and comets passing through it undisturbed. The aether was, in its own way, a return to the old intuition that emptiness could not truly be empty, dressed now in the language of mechanics rather than philosophy. It needed to be rigid enough to support the extremely rapid oscillations of light, yet so insubstantial that it offered no detectable resistance to anything moving through it, a combination of properties that grew more strained the more carefully physicists examined it. Experiments designed to detect the Earth's motion through this supposed medium. Most famously, an experiment conducted in the 1880s by two American physicists using an extraordinarily sensitive optical apparatus searched for the faint signature that the ether's presence should have produced. They found nothing. No drag, no shift, no trace of any medium at all. The experiment was repeated, refined, and repeated again, and the result remained the same null outcome each time, an absence of evidence that grew more difficult to explain away the longer it was tested. By the final years of the 19th century, the ether had become a hypothesis kept alive more by the absence of an alternative than by any evidence in its favor. Physicists had built an entire physical substance into the universe for the sole purpose of carrying light, and the universe had declined to confirm its existence at every opportunity offered to it. The collapse, when it came, was not dramatic in the way later physics would come to associate with paradigm shifts. There was no single experiment that delivered a final verdict, no announcement that closed the matter definitively in public view. Instead, the ether faded out of serious consideration gradually, displaced by a new way of describing light and motion that required no medium at all, one in which the speed of light was simply a constant feature of the universe rather than a property of some hidden substance propagating it. The number entered physics through a problem that had nothing to do with light or motion and everything to do with a question that had never been properly asked before any theory existed capable of asking it. What shape was the universe as a whole, taken in its entirety, and did that shape change over time or remain fixed? Albert Einstein, having completed his general theory of relativity in the final months of 1915, turned his attention to this question within 2 years of finishing the theory itself, applying his own equations to the universe at large rather than to the more modest problems of planetary orbits and falling bodies that had occupied him until then. What he found troubled him. General relativity described gravity as a curvature in the fabric of space and time, produced by the presence of matter and energy. And when Einstein applied this description to a universe filled more or less evenly with matter, the equations refused to produce a stable, unchanging result. Matter attracts matter. A universe filled with galaxies pulling on one another gravitationally should, according to the mathematics, either be expanding or contracting, never sitting motionless, because gravity offers no mechanism by which mutual attraction can hold a system in permanent stillness. The equations were not ambiguous on this point. They described a dynamic universe, one in motion, and Einstein found this conclusion difficult to accept. The difficulty was not mathematical, but cultural, in the broadest sense of that word. Nearly every astronomer working at the time understood the universe as fundamentally static, an unchanging arrangement of stars within a fixed cosmic backdrop, much as Newton's absolute space had once been understood as a permanent and motionless container. The available observational evidence, limited as it was in 1917 to the stars visible within a single galaxy, gave no indication of any large-scale expansion or contraction, and there was no observational pressure pushing physicists toward a dynamic picture. Einstein, working from this inherited assumption of a static cosmos, treated his equations' refusal to support that assumption as a flaw to be corrected rather than a discovery to be reported. His correction took the form of a single additional term inserted into the field equations of general relativity, a constant of a particular kind, one representing a uniform energy density, spread evenly throughout space itself, exerting a repulsive effect strong enough to counterbalance the inward pull of gravitating matter. He called it the cosmological constant, and its sole purpose, as he conceived it in that original context, was to hold the universe motionless, to provide exactly enough outward pressure to cancel exactly the amount of inward collapse that the matter in the universe would otherwise produce. The balance required was delicate. The constant could not be too large or too small. It had to be tuned with precision to the total density of matter in order to achieve the static result Einstein was seeking. And this need for precise tuning was itself a feature he was willing to accept in exchange for a universe that matched the unchanging picture everyone, including himself, expected to be true. There is something worth noticing in this moment, that later accounts of the story sometimes pass over quickly. Einstein did not introduce the cosmological constant because his equations demanded it. He introduced it because his equations produced an answer he did not believe, and he altered the mathematics until it produced an answer he did. The constant was not a prediction, it was a patch, applied to preserve an assumption that turned out, within a decade, to be the part of the picture that needed to be discarded rather than protected. The static universe Einstein had worked to preserve did not survive long. Independent theoretical work by other physicists during the early 1920s, exploring solutions to the same general relativity equations without insisting on a static outcome, demonstrated that an expanding or contracting universe was a perfectly natural and stable solution in its own right, requiring no delicate balancing term to remain coherent. These theoretical explorations met with skepticism at first, including skepticism from Einstein himself, who initially dismissed one such proposal as containing a mathematical error before later acknowledging that the mathematics was sound even if he remained unconvinced the universe actually behaved that way. The observational evidence that settled the matter arrived from an American astronomer working at a mountain observatory in California during the second half of the 1920s. Using one of the most powerful telescopes available anywhere in the world at the time, he measured the light arriving from a large number of distant galaxies and found that this light was systematically shifted toward longer, redder wavelengths, an effect consistent with those galaxies moving away from our own. More strikingly, he found that the more distant a galaxy appeared to be, the greater its redshift, meaning the more distant galaxies were receding faster than the nearer ones. This relationship between distance and recession speed was not scattered or inconsistent. It held across galaxy after galaxy, forming a clear pattern that admitted only one reasonable explanation. The universe itself was expanding, carrying galaxies apart from one another as space between them stretched. The announcement of this finding, made public in the closing years of the 1920s, did not merely add a new fact to astronomy. It removed the entire justification for the term Einstein had inserted into his equations a decade earlier. A universe that was demonstrably expanding had no need of a repulsive force calibrated to hold it still, because it was not still and never had been. The cosmological constant, introduced for the express purpose of producing a static result, became an answer to a question that observation had just shown was the wrong question to have asked. Einstein's response to this turn of events has become one of the most frequently repeated anecdotes in the history of physics, recounted by colleagues who heard him describe the cosmological constant in later conversations as the greatest blunder of his scientific life. Whether he used precisely those words in precisely that context is a detail historians have debated, since the remark survives primarily through the recollections of others rather than in his own written record, but the substance of his regret is not in dispute. He had altered a theory that, left alone, would have anticipated the expansion of the universe more than a decade before any telescope detected it, and he had altered it specifically to avoid a conclusion that observation would soon prove correct. The constant was removed from serious consideration, treated from that point forward as an unfortunate detour, a number invented to solve a problem that observation later revealed had never existed. The framework that would eventually return to Einstein's abandoned number did not emerge from astronomy at all, but from a far smaller arena, the study of how particles and forces behaved when described not as isolated objects moving through a passive backdrop, but as disturbances in fields that filled all of space without exception. Quantum field theory, developed and refined across the middle decades of the 20th century by physicists working in close conversation with one another across many countries, proposed something that the earlier history of empty space had never quite anticipated. that the vacuum was not the absence of fields, but their ground state, the lowest level of activity a field could reach while still remaining a field, present everywhere whether or not any particle could be detected within it. This was a more radical claim than it first appears. A field with no particles in it under this framework was not equivalent to nothing. Quantum mechanics, applied to fields rather than to point particles, forbids any field from settling into perfect, motionless stillness, because doing so would require specifying its value and its rate of change simultaneously with total precision, a violation of the uncertainty principle that governs every quantum system. Instead, even in its emptiest possible configuration, a field continues to fluctuate, with particles and their antiparticles flickering briefly into existence in pairs before annihilating each other again, a process occurring constantly throughout every region of space, including the regions a casual observer would describe as perfectly empty. The vacuum, in this telling, was not a stage. It was an arena of restless, low-level activity that never fully ceased. These fluctuations were not merely a theoretical flourish invoked to make the mathematics behave. Physicists found ways to detect their physical consequences directly, an effect named after the Dutch physicist who first calculated it in detail during the late 1940s demonstrated that two uncharged metal plates placed extremely close together in a vacuum with nothing between them would experience a measurable attractive force, produced because the plates restricted which vacuum fluctuations could occur in the narrow gap between them compared to the unrestricted space outside. This force was eventually measured in laboratories with increasing precision across the second half of the 20th century, and its existence confirmed, beyond reasonable doubt, that the empty space between those plates was doing something, exerting a real, measurable influence on the objects bounded by it. The vacuum, far from being inert, had a physical reality that could be felt and quantified. If the vacuum possessed this kind of restless activity, then it followed, almost unavoidably, that it should possess an energy density of its own, a definite numerical value describing how much energy was packed into every unit of empty space as a consequence of all these fleeting fluctuations occurring across every field simultaneously. This was precisely the quantity that Einstein's cosmological constant had described decades earlier, treated then as a free parameter that could be set to whatever value made the equations agree with observation. Quantum field theory offered something Einstein's original formulation never had, a method for calculating that value directly from first principles, by summing the contributions of every known field's fluctuations across every scale of distance the theory could describe. When physicists carried out this calculation in earnest, beginning in the latter half of the 20th century as quantum field theory matured into its modern form, the result was not simply large. It was large in a way that strained ordinary description. The predicted energy density of the vacuum, summed across all the fields the standard model included, exceeded the energy density that would actually be required to match a universe with any plausible cosmological behavior by a factor that ran to 120 orders of magnitude, a number written as a 1 followed by 120 zeros. There is no everyday comparison capable of conveying a discrepancy of this size. It is not the difference between an estimate and the correct answer, in the way an inaccurate guess might be wrong by a few percent, or even by many multiples. It is a difference so vast that physicists working in other fields, encountering it for the first time, have often assumed it must be a typographical error before confirming that the figure is reported correctly. This discrepancy became known within the discipline as the cosmological constant problem, and it represented something genuinely unusual in the history of physics, a calculation performed correctly using a theory that had otherwise proven extraordinarily successful at predicting the outcomes of countless experiments, arriving at an answer that disagreed with reality by a margin large enough to qualify, by most informal reckonings among physicists themselves, as the worst quantitative prediction ever produced by a serious scientific framework. The theory was not flawed in any way that showed up elsewhere. Quantum field theory predicted the behavior of particles in laboratory experiments with extraordinary accuracy, matching measurement after measurement to many decimal places. It was only when the same methods were turned toward the vacuum's total energy that the answer broke apart so completely. The natural response for many physicists confronting this problem across the final decades of the 20th century was to suspect that some unknown mechanism must be canceling the enormous predicted value down to something near zero, a hidden symmetry or compensating effect not yet accounted for in the calculation. This suspicion was reasonable, and it shaped decades of theoretical work searching for exactly such a mechanism. What made the search frustrating was the absence of any candidate symmetry within the existing framework capable of producing a cancellation this precise, one that would need to erase 120 orders of magnitude while leaving behind a residue small enough to match what little cosmological evidence then existed, without simply erasing the vacuum energy down to exactly nothing in the process. No such mechanism revealed itself, and the problem remained. Through the closing years of the 20th century, one of the most conspicuous open wounds in theoretical physics, acknowledged widely but resolved by no one. A second number, arrived at through an entirely separate line of inquiry, would soon compound the unease surrounding the vacuum without resolving it. The standard model of particle physics, completed in its essential structure by the middle 1970s and confirmed piece by piece across the following decades, predicted the existence of a particle responsible for giving mass to many of the other particles within the theory, a particle that remained undetected for nearly half a century after it was first proposed. When this particle was finally confirmed experimentally in the early 2010s, its measured mass carried an implication that few outside the field appreciated at the time of the announcement. Combined with the separately measured mass of the heaviest known quark, the Higgs boson's mass placed the vacuum, according to the equations governing the stability of quantum fields, in a condition physicists describe as metastable, a state resembling a shallow depression partway up a slope rather than the deepest point of a valley floor, stable enough to persist for an extraordinarily long span of time, yet not sitting at the lowest energy configuration the underlying mathematics would technically allow. While theorists wrestled with a calculation that refused to match anything observable, two independent teams of astronomers, working through the 1990s with no particular allegiance to the cosmological constant problem, were pursuing a far more modest goal, measuring how quickly the expansion of the universe was slowing down. The assumption guiding both teams was one that had gone essentially unquestioned since the era of the static universe had given way to the expanding one. Gravity pulls matter together. An expanding universe filled with galaxies, all attracting one another, should therefore be decelerating, its outward rush gradually losing momentum against the inward pull of its own mass, much as a stone thrown upward slows under the steady drag of gravity before eventually reversing course. To measure this deceleration, both teams turned to a particular category of stellar explosion, a class of supernova produced when a dense, compact stellar remnant accumulates matter from a companion star until it crosses a precise threshold and detonates. These explosions reach a strikingly consistent peak brightness across the universe, a consistency that makes them valuable as distance markers, since any variation in how bright one appears from Earth, once its true brightness is known, can be attributed almost entirely to how far away it lies. By observing many such explosions at a wide range of distances and comparing their apparent brightness to the redshift of the galaxies hosting them, astronomers believed they could chart how the rate of cosmic expansion had changed across billions of years of history, reading the universe's deceleration directly from the pattern in the data. The data, when both teams independently completed their analyses near the end of the 1990s, did not show deceleration. Distant supernovae appeared fainter than they should have if the universe's expansion had been slowing down at any point since the explosions occurred. Fainter, in a way consistent with an expansion that had been speeding up rather than winding down. The implication ran directly against the assumption every astronomer in both groups had carried into the project. Something was pushing the universe apart with increasing force, overpowering the gravitational pull of all the matter contained within it, and that something was distributed evenly enough across space to produce the same accelerating effect in every direction the telescopes were pointed. The announcement, made public in 1998, returned the discipline to a term that had spent 7 decades treated as a historical footnote rather than a live possibility. A uniform repulsive effect, present everywhere, capable of overpowering gravity at cosmic scales, was precisely the kind of behavior the cosmological constant had been built to produce, even though Einstein had inserted it for a purpose, holding a static universe still, that the very astronomers reviving it understood to be entirely mistaken. The constant came back not as a patch to preserve an assumption, but as a description that fit the data better than any available alternative. measured rather than postulated, observed rather than required by an a priori commitment to what the universe ought to look like. Physicists adopted a new name for whatever this repulsive effect represented physically, calling it dark energy, a label deliberately broad enough to cover the possibility that the effect was indeed the cosmological constant in its simplest form, a fixed and unchanging energy density built into the structure of space itself, or alternatively, some other phenomenon, perhaps a field capable of varying across time and location rather than remaining perfectly constant, that merely resembled a cosmological constant within the precision current instruments could achieve. The simplest mathematical description, treating dark energy as exactly equivalent to Einstein's original term, fit every subsequent observation with remarkable consistency, and across the decades following the initial announcement, increasingly sophisticated surveys of the cosmic microwave background, the large-scale distribution of galaxies, and additional supernova catalogs continued to confirm that this simple description matched the universe's behavior to a high degree of precision. This left the discipline in a position that was, in its own way, more uncomfortable than total ignorance would have been. The cosmological constant was no longer a speculative term that could be dismissed or set to zero without observational consequence. It was a measured feature of the universe, pinned down by multiple independent lines of evidence to a specific non-zero value. And that measured value remained exactly as incompatible with the value predicted by quantum field theory's calculation of vacuum energy as it had been before the supernova surveys existed. The cosmological constant problem had not been solved by the discovery of dark energy. It had been sharpened, because the side of the equation that observation could constrain was no longer an open question awaiting data. The mismatch between prediction and reality, previously a disagreement between a calculation and an assumption that the true value was probably near zero, had become a disagreement between a calculation and a number measured directly from the sky, a number very small but unambiguously present, and very far from anything the underlying theory of fields could account for through any mechanism yet identified. The decades following the 1998 discovery produced no resolution to this mismatch, despite sustained theoretical effort pursued from several directions at once. Some physicists pursued the possibility that an undiscovered symmetry, operating at an energy scale beyond anything tested in laboratories, might enforce the necessary cancellation precisely enough to leave behind the small residual value observed in the sky, though no such symmetry had been identified within any framework consistent with existing data. Others pursued an explanation grounded in selection rather than mechanism, an argument holding that the cosmological constant might take a wide range of different values across different regions of a much larger universe or multiverse, and that observers capable of asking the question at all could only ever find themselves in a region where the value happened to be small enough to permit the formation of galaxies, stars, and the chemistry required for life. This second line of reasoning, often associated with the anthropic principle, offered a kind of explanation for why the observed value might be what it is, without offering any mechanism rooted in the equations of physics themselves, a feature that left much of the discipline unsatisfied even among those who found the argument logically coherent. Neither explanation achieved anything resembling consensus, and the cosmological constant problem entered the 21st century carrying the same status it had carried at the close of the 20th. Acknowledged by nearly every physicist working in the relevant fields as a genuine and unresolved difficulty, discussed openly in textbooks and conference proceedings, and yet absent any agreed path toward resolution. What had changed was the broader context surrounding the problem. The metastable classification of the vacuum, established through the Higgs boson's measured mass, sat alongside the cosmological constant's unexplained smallness as a second open question concerning the same underlying subject, the actual energy state occupied by empty space, and a growing number of theorists began to treat these as related symptoms rather than coincidentally adjacent puzzles. Both questions concern the same physical quantity, the vacuum's energy, examined through different theoretical lenses and arriving at different specific difficulties, and the frameworks proposed to address the hierarchy between gravity and the other forces. The same frameworks invoked to explain why the Higgs boson's mass sits where it does, frequently carried implications for the cosmological constant as well, suggesting that a single deeper mechanism, not yet identified, might be required to settle both accounts simultaneously rather than two unrelated mechanisms addressing each in isolation. What remains? after tracing this number across so many different hands and so many different centuries, is not a settled answer, but a settled pattern, one visible only from the distance this account has tried to maintain. Each era that took up the question of empty space did so with the complete confidence available to its own moment, certain that its instruments and its mathematics had finally captured something true about the backdrop against which all other events unfolded, and each era, in turn, discovered only after the fact that some essential piece of its confidence had been misplaced. Aristotle's reasoning was not careless, yet it mistook the absence of a resisting medium for a logical impossibility. Newton's absolute space was not naive, yet it treated as eternally fixed a geometry that later proved to bend and stretch in the presence of mass. The ether was not invented out of foolishness, yet an entire physical substance was built into the universe to solve a problem that required no substance at all. Einstein did not insert his constant carelessly, yet he shaped his own equations to avoid a conclusion that the sky would soon insist upon, regardless of his preference. Quantum field theory did not calculate carelessly, yet its most direct prediction about the vacuum's energy stands, to this day, as the least accurate forecast that framework has ever produced about anything. None of these were failures of intelligence or rigor. They were the ordinary condition of working at the edge of what a given era's instruments could reveal, mistaking the limit of detection for the limit of reality, and finding out only later, often decades later, exactly where that limit had been. The pattern does not suggest that the current understanding, with its measured cosmological constant and its metastable vacuum sitting near an unresolved boundary, has finally escaped this condition. It suggests, if anything, that the current understanding occupies the same position every previous understanding once occupied, confident within the range its instruments can reach, uncertain about everything that range cannot yet touch, and unaware, in ways that will only become visible from some future vantage point, of which of its present convictions will eventually be set aside. What carried forward across every one of these transitions was never the model itself, but the willingness to test it against whatever new instrument or new observation became available. The mechanical pump that emptied Aristotle's vacuum, the telescope that measured the galaxies receding from Newton's absolute frame, the interferometer that searched for an ether and found none, the redshift survey that revealed an expansion Einstein had tried to equation away, and the calculation that exposed, with uncomfortable precision, exactly how far quantum field theory's predictions stood from the value the universe actually carries. Each instrument did not merely refine the previous picture. It replaced some load-bearing piece of that picture entirely, while leaving other pieces, the basic mathematics of motion, the structure of fields, the methods of measurement themselves, intact and carried forward into whatever came next. The history of the vacuum is, in this sense, a history of demolition and preservation occurring simultaneously, every era discarding something its predecessors had trusted while keeping enough of the surrounding framework that the next era could begin its own work without starting over from nothing. The present moment in this history is occupied by an experimental program currently underway in a tunnel beneath the border of 2 European countries, where measurements of the Higgs boson's mass and the mass of the heaviest quark are being refined with a precision no earlier generation of physicists could have achieved. Work that will either move the metastable classification closer to the boundary, separating it from full stability, or push it further away, narrowing, in either direction, a question that has remained open since the particle's discovery. Anyone interested in following how this particular chapter develops, as the measurements continue to sharpen in the years ahead, may find it worthwhile to seek out ongoing reporting on the subject and to remain engaged with how the account continues to unfold. What the long arc traced here ultimately offers is not a destination, but a disposition, a way of holding the present picture of empty space with the same seriousness every previous picture deserved and received, while remembering that seriousness has never once been sufficient to make a picture final. The vacuum has been feared, then fixed, then filled, then emptied again, then weighted with a number its own author came to regret, then recalculated into the largest error physics has ever produced, then measured directly in the light of exploding stars billions of years old. And at every stage along that path it was understood, by the people doing the understanding, as essentially settled. It was not settled at any of those stages, and there is no particular reason to assume that the understanding held today, however supported by precision instruments and decades of confirmed calculation, has finally arrived at the exception to a pattern that has held without interruption for over 2,000 years of inquiry. The The question of what empty space actually is, and whether it is stable in the way that everything resting upon it would need it to be, remains exactly what it has always been at every point in this account: open, inherited, and still, after all this time, unanswered.